piecewise defined functions are exactly what their name implies. They are functions that are defined in pieces. There are a lot of applications where there's some sort of a transition in the formula that you should use for whatever it is you're trying to describe with your function. And so we set it up where it has the appropriate function formula over the specified span of input values. And then we can also graph a piecewise defined function to get an overall view of what's going on in these individual pieces. One example could be like with the Postal Service. If you have a letter that you're mailing and it's less than and up to an ounce, it's a specific stamp value that you have for that. Now if you go over the ounce by a little bit, but up to and including 2 ounces, then you have a different value that you have to put onto the letter for the postage. And that additional ounce is not at the same rate as the original first ounce of what you were mailing. So there we would have our output for the cost of mailing that letter that would have different values over spans of those specific inputs. What I'd like to do in this video is show you an example of a piecewise defined function and how you are able to get the graph of it, as well as answering questions about what the output of the function is at specific given inputs. So our first example is the piecewise defined function f of x is equal to 3x minus 1 over the span of x's that are less than or equal to negative 1. It's equal to x squared minus 2x if you're plugging in the span of x's that are greater than negative 1 but less than or equal to 3. And the function output is equal to 7 when the x's that you're putting in are values that are greater than 3. So the thing about this is when you're trying to ask yourself, well, how am I going to evaluate the function at a given input, the first thing you have to look at is this right end of the definition of each of the pieces and find out which one of these include the input that you're supposed to find the function value for. And then once you find out where your input lies, then you know what rule you would use to get the output there. Here, let's see an example. So the first one is to take this function and find f of 2. So this means go to your function, take out the x's, and put in 2 instead. Well, 2 is not a number that is less than or equal to negative 1, so I'm not going to use that first rule. 2 is a number that lives between greater than negative 1 and less than or equal to 3. So 2 is in this span of x's. So the x squared minus 2x is the rule I will use when I'm asked to find the output when 2 is put in for the x's. So my f of 2 is going to be 2 squared minus 2 times 2. So then I get f of 2 is 4 minus 4. Following order of operations, 2 squared is 4, minus 2 times 2 is 4, and 4 minus 4 gives me 0. So when I put 2 in through this function, that input is in the span where the definition of the function there is x squared minus 2x. So then to find f of 2, we take out the x's in that piece of the rule and then get our output. How about f of 9? Well, here it's asking you to find the function value when your input is 9. Well, 9 is not less than or equal to negative 1. 9 is not a number that's bigger than negative 1 but less than or equal to 3. 9 is a number that's bigger than 3. So the rule I should use for this one is that my f of x is equal to 7. So f of 9, well, here there is no x to take out to put the 9 in instead. Over that span of x's, my output is always 7. No matter what number greater than 3 your input is, you're always going to have an output of 7. So f of 9 is 7. Now let's see how we'll get the overall picture. The graph of this function called f of x. Well, since it is a piecewise defined function, I want to think of what the individual pieces are and then graph them individually, but putting those individual pieces on the same plane. So first of all, for the x's that are less than or equal to -1, if I'm plugging in x values, input values that are less than or equal to -1, then my rule is that f of x is equal to 3x minus 1. So f of x is just another name for y. I'm going to write this as y is equal to 3x minus 1. When my input is a number that is less than or equal to -1. Now, I can make a table of values for this just to kind of really see how it's going. But if I do make a table for this, you want to be very careful to plug in the appropriate inputs for that span. So this says I have to put in numbers that are less than or equal to -1. So since it's less than or equal to -1, I'm going to plug in -1, and values that are less than -1 would be like -2 and -3. So we're going to put in -1, -2, and -3. Now, this equation, y equals 3x minus 1, is actually a linear equation. So for that piece of the function, that piece is a line. And that piece is a line, so I only really needed to do 2 ordered pairs and just put my straight edge down and connect them, but I did the extra value of x just to make sure. And you'll always want to include the value of x that is the transition value of the input from either the one end of it or start and finish of it, just so you make sure that you get the complete graph. All right, so what happens if I put -1 in for the x? Well, that gives me 3 times -1 and then -1. So that's -3 minus 1 more is -4. How about if I put -2 in for the x? That's 3 times -2, then -1. So that would be -6 minus 1 is -7. And then if I put -3 in for the x, that'll be 3 times -3 minus 1. Or -9 minus 1 is -10. So I have those particular dots for just that piece, but this is just for the x's that are less than or equal to -1. So when I think of my origin here, an x value of -1 is one left of the origin, so this piece is only from that x value over here. I can't extend it any further beyond x equal -1 because that rule is not valid beyond -1. Values bigger than -1. So let's graph these points. Now this had the or equal to, so I'm going to put the dot at -1 comma -4. That's your ordered pair when you make the table. So left 1 down 4 is here. And then -2, -7, so I'm going to go left 2 down 7. And then left 3 down 10. And now when I use my straight edge and I connect it, I can only connect it to the left of x equal -1. So that's the first piece. So now what about for the x's that are greater than -1 but less than or equal to 3? So just over that span. So -1 and then an x value of 1, 2, 3. So it's just going to be in here where that is. Well, y equal x squared minus 2x is a parabola. And it is a parabola that we could also go through and find its x-intercepts, and we could find its vertex, but we would only graph those parts if they were in the span of the x's that we're allowed to plug in for this. Now let's go ahead and make a table again instead. So we're going to make our table x comma y, and then With this, remember, this is a parabola. It curves. So since it curves, I need more than just 3 dots. I need at least about 5 well-chosen dots. Now, because this span is greater than -1 but less than or equal to 3, I still want to plug in the inputs that start and finish the interval for which that rule is valid. But without the or equal to, I want to remind myself somehow visually that at x equal -1, the rule was this other rule, the 3x minus 1 rule. But I've got to get like infinitely close to it, and this one has to start infinitely close on the other end of it. So we're still going to plug in -1. It's just that we're going to remind ourselves that there was not an or equal to here, so that when we plot the dot of that ordered pair, we're going to use an open circle instead of filled in dot. And you only have to worry about the open circle and the filled in dot at those transition inputs between one part of the piecewise defined function to the other. So like here at the -1 at the 3. So here for -1, I'm going to remind myself it doesn't have the or equal to by making like a dashed -1 that I plug in, and that'll remind me visually that I should plot that dot with an open circle. Now, if we plug -1 in for the x's, that would be -1 quantity squared minus 2 times -1. Well, -1 quantity squared is 1, and -2 times -1 is +2. 1 plus 2 is 3. So I'm also going to make the 3 kind of like a dashed work, and then that, again, like I said, reminds me that there's an open circle there instead of a filled-in dot. How about when x is 0? X equals 0 is a number in the span from -1 to 3. 0 squared minus 2 times 0 is 0. So 0, 0 is on that parabola. How about when x is equal to 1? Well, if x is equal to 1, that's 1 squared minus 2 times 1. So that's 1 minus 2. 1 subtract 2 is -1. When x is equal to 2, well, we calculated that over in part A. When x was equal to 2, we got a value out of 0. And then we still want to also do 3, and this has the or equal to. So we're going to do a filled-in dot for that one. So I'm going to make my notation just a regular solid writing to remind myself it's a filled-in dot there. So when x is 3, we get 3 squared minus 2 times 3. So 3 squared is 9. 9 minus 6 gives me 3. So now we'll go ahead and graph these dots. So at -1 comma 3, at left 1 up 3, I'm going to have an open circle. And again, it's because it didn't have the or equal. And then we have our 0, 0. We have 1, -1. We have 2, 0. And we have 3, 3. But 3, 3 is a filled-in dot because it had the or equal. And I've got my parabola there. So this case, if I would have found the x-intercepts and the vertex, they would have been in the span of x's that it was valid, and would have been something else that I could have used in order to graph that. Now the last piece of this is for the x's that are greater than 3. So for the x values that are greater than 3, our rule is that f of x is equal to 7, or I can write y equals 7. So this piece of it is just for over the spans where it's valid, a horizontal line. And when I make just a couple values in my table, and I want to do the cutoff number 3, notice it doesn't have an or equal to. So there's going to be an open circle at the spot 3, 7. So if I plug in a 3, I'm going to do it dash to remind myself it didn't have the or equal to. and y is 7 throughout all of this piece of it. So 3, and then another number that's bigger than 3 is like 4, and I'd also get out 7, and 5, and I'd also get out 7. So when I go to right 1, 2, 3, up 1, 2, 3, 4, 5, 6, 7, I'll have an open circle and then the horizontal line. So this entire picture is the picture of your piecewise defined function, and it's a piecewise defined function. It has to pass the vertical line test. So when you're looking and imagining all the possible vertical lines you could draw, even like right here, it's open and closed, so that's only hitting it at one spot. Here, it's only hitting it at one spot. Your pictures have to pass the vertical line test if you're drawing a graph of a function. So if you've tried to do the piecewise defined functions and you look at your picture and it doesn't pass the vertical line test, you have to think to yourself, I forgot to only graph my pieces over the span of x's for which they were valid, so I need to go back and erase off the parts that I shouldn't have continued on with the graph. Now another thing is we can verify what we got for our function values actually looking at the graph. So this asks me to find f of 2. So what is the output of the function when x is 2? So I could go to 1, 2 for my x, and my output is 0. So f of 2 is 0. This is asking me for f of 9. What is the output of my function when x is 9? So when I go 1, 2, 3, 4, 5, 6, 7, 8, 9, it would be 7. If they asked me to find f of negative 1, I didn't have it as one of our options, but it's a good thing to discuss and just make sure we see it. If they asked me to find f of negative 1, I can look over here and realize that my value that's valid when x is negative 1 is the filled in dot, not the open circle. So f of negative 1 gives me an output that is negative 1, negative 2, negative 3, and negative 4. So f of negative 1 is negative 4. All of those values. And I could have actually also looked back at my tables or a lot of different ways to do that. But if they just give you the graph of the piecewise defined function and they ask you to find the function values of each of these, then that's how you would read them off the graph. So next up, we're going to look at another example of a piecewise defined function. Take another look at a piecewise defined function and just get some more examples under our belt. Here we have the piecewise defined function that is the absolute value of x plus 1 for x less than 1, the opposite of x minus 2 squared plus 1 for x values that are from 1 to 3, and then negative 2x plus 5 for the x's that are greater than 3. So when I'm looking at this, I want to make sure that I see that thinking about x values from small to big, that it's kind of been organized where these would be smaller x's and then building towards larger ones, just so I see that whoever was writing the question organized it in a way that it makes sense when we're going through it. Now, if it's not organized that way, you can still be successful working with the graph of it. It just is something that you just have to tread much more carefully to make sure that you graph it over the spans that are appropriate. Both of my examples have had 3 pieces to them, but it doesn't have to. You can have a piecewise defined function that has 2 pieces or 3 pieces up to 100 pieces. I mean, there's no limit to it. So just make sure that you realize that I've just done piecewise defined function with 3 pieces to give you a good enough understanding of what to do for the different pieces, but also do them quick enough that I could give you more than one example. So here we have our piecewise defined function. It's equal to the absolute value of x plus 1 for the x is less than 1, like I said, and each of these other pieces as we've already gone through. And now find f of 1. So for f of 1, I need to look at the input they're asking me about, and they're asking about the input 1, and I need to find out where I have it that the rule is valid for x equal 1. Well, the x less than 1 does not include 1, so it's not going to be the first rule. The x equal 1 is a number that is 1 less than or equal to x less than or equal to 3. It's got the or equal here. So this middle rule is the one that I'm going to use for this first question. So we'll take out the x and put in 1. So that's the opposite of 1 minus 2 quantity squared and then plus 1. So f of 1 is the opposite of, remember your order of operations. You have to do what's inside parentheses first. 1 subtract 2 is a negative 1, quantity squared, and then plus 1. Then you have to do exponents. So negative 1 quantity squared is positive 1. And then after you do that exponent, then apply the minus. So my f of 1 is the negative 1 and then plus 1. So f of 1 is 0. So when x equals 1, 0 comes out for my function value. Now it asks me to graph it. So we're going to start with, for the x's that are smaller than 1, my rule is y equal the absolute value of x and then plus 1. So making a table, remember I want several different values. Remember the absolute value function is a v. So you can't just do a couple, you've got to do several different ones. Since it's just the absolute value of x without any plus or minus in the absolute value with it, I don't have a horizontal shift, but I do have a plus 1 after the absolute value, so I do have a vertical shift. So when I plug in some values, I probably want to go like negative 2, negative 1, 0, and this doesn't have the or equal to, so I'm going to put the 1 in dashed to make sure I remember to do the open circle there. So plugging each of these in, the absolute value of negative 2 and then plus 1. Well, the absolute value of negative 2 is 2. 2 plus 1 is 3. Now plug in negative 1. It's the absolute value of negative 1 and then plus 1. Well, the absolute value of negative 1 is 1 and 1 plus 1 is 2. And then when I look at 0, the absolute value of 0, then plus 1, comes out 1. And make sure it looks like the absolute value. And then plug in a 1. So the absolute value of 1 plus 1, and we'll actually make that dashed also. Well, the absolute value of 1 is 1, and 1 plus 1 is 2. But I'm going to make a dash to remind myself to do the open circle there. Okay, now how about for the x values that are 1 less than or equal to x less than or equal to 3. So I have to read these kind of from the right back towards the left when I'm doing the problems. And I think that sometimes is what kind of trips us up. We're used to reading stuff from left to right so much that we forget that with the piecewise defined function, you got to figure out what your inputs are on the right hand side before you come over to see what the rule is that you would use to get your output. Now for the x's that are from and including 1 to 3, my rule is y equal the negative of x minus 2 squared and then plus 1. And this would ultimately have a square on my x, so that would be a parabola. Its outside number is a negative, so it's going to be a parabola going down. And it's actually in vertex form. The vertex of this parabola is going to be 2, 1. So I see 2, 1 as my vertex. 2 is a number that's between 1 and 3. So I could use that information about the vertex in order to get a nice picture of the parabola. But let's go ahead and just make our table. And then it's or equal to on both of these. So I'm going to have the 1 and then the 2 and then the 3 and then stop at that. So when you plug a 1 in, that's the opposite of 1 minus 2 quantity squared and then plus 1. Follow your order of operations. 1 minus 2 is negative 1. Negative 1 squared is 1. The opposite of 1 is negative 1 plus 1 gives me a 0 out. And that's what we did over here. We already had that. F of 2, if I put 2 in for my x's for this rule, that's the opposite of 2 minus 2 quantity squared plus 1. Well, 2 minus 2 is 0. 0 squared 0. The opposite of 0 is still 0. And then 0 plus 1 is 1. And then if I were to put 3 in, it's the opposite of 3 minus 2 quantity squared and then plus 1. So 3 minus 2 is 1. 1 squared is 1. The opposite of 1 is negative 1. Negative 1 plus 1 is 0. And then lastly, we have our function f of x is equal to the piece negative 2x plus 5 for the x's that are bigger than 3. So for my x's that are greater than 3, my y is negative 2x plus 5. So when I make my table, I'm going to dash a 3 in there and then also put in 4. But I just need to do those two values of x run through because it's a line and I only need 2 points to determine a line. So put in your 3. Negative 2 times 3 is negative 6 plus 5 is a negative 1. Put a 4 in there. Negative 2 times 4 is negative 8. Negative 8 plus 5 is negative 3. And again, I dashed those to remind myself there's an open circle because it didn't have the or equal to. So now let's graph the pieces. So my first one, I have left 2 up 3. And then left 1 up 2. Don't go left to right, go up 1. Right 1, up 2, but do an open circle. That's what the dash thing reminds you of. So my piece that is the absolute value and the turn of it is actually in the span of x's that it's valid for. Looks like that. The next one I have 1, 0. So go right 1, don't go up or down, and fill it in because we had the or equal to. Then 2, 1, and then 3, 0. And that's it. It's only valid from 1 to 3. So we have our parabola, but just that piece of it. And then for the x's that are greater than 3, I'm going to have a open circle at 3, negative 1. So write 1, 2, 3, negative 1 is an open circle. And then at 1, 2, 3, 4, negative 1, 2, 3. I have a dot to get my span to do the line. So you see that, again, it's going to pass the vertical line test. Even at the points where I have the transition, I've got one filled in, the other one open. They could both be open. There could be x values that aren't in the domain of your piecewise defined function if there might have been one where they both don't have the or equal to, but they can't both be filled. If they're both filled and they're at the same x, then that wouldn't be a function, so they wouldn't have been able to use function notation on the question.